Alright, so the last sections have more to do with applications of the fundamental theorem of calculus and areas, but we're going to expand it to areas between curves and then get to a special type of application that we're going to look at in 5.5 called consumer surplus and producer surplus, which again we'll get to those when we get to that section. Alright, so this is the procedure to find the area between two curves using the definite integral and the fundamental theorem of calculus. Alright, so suppose I have two functions. Alright, both of them are continuous. Again, it works for our functions are continuous over our interval. Alright, if we know that one function, so in this case I said f of x, was bigger than g of x for everywhere that we're looking at. Alright, so between our values a and b. Alright, so that would be where the area we're looking between. Then we can find the area between the two functions by integrating the area underneath the function where I've taken the bigger function minus the little function. Alright, and so I'm actually going to do two different graphs here. I'm going to show you the original and then what happens when we're integrating. Alright, so I'm going to start with the original two function with two curves. Alright, and so the original function would be, well, I have some f of x, some g of x, alright, and I'm integrating and I want to know between a and b. Alright, so a and b would be my starting and stopping points. And I want the area between my two functions from a to b. So this would be the f of x, the bigger function. This would be, so I'm bounded by f of x, which is the bigger function, and g of x, which is the lower function. Alright, so it doesn't have anything to do with my axes right now. The area under a curve and the x-axis. Alright, so I can't find this directly because the fundamental theorem of calculus is accumulation of under my function with the x-axis. Well, I want to know what the accumulation is between my two function values. And the process to do that is, well, what I do is I take the bigger function and I subtract away the littler function. And I am, in essence, creating a whole new function. I'm taking f of x minus g of x, right? That's what we're doing here. We're taking f of x minus g of x to find this area. And so what happens when we take, so suppose I call it a new function. I call h of x the new function, f of x minus g of x. Okay, we're taking the bigger function and subtract away the little function. What that does is it creates a new function. Alright? And again, I'm just randomly drawing a new function. So there would be my h of x, which represents f of x minus g of x. Alright, and now this area, now it has a different shape, but I can now find this area because now it's bounded by the x-axis and a function using the fundamental theorem of calculus. And this area, even though it's a different shape, is the exact same as that area. So both of these areas are the same size areas. This one I can solve with the fundamental theorem of calculus. I can integrate from a to b of h of x using the fundamental theorem of calculus. Alright, and so that's what this is allowing me to do. So again, it's a very simple thing. It's very subtle. I just take the bigger function minus the littler function. But there's a lot of interesting things going on. Like I said, it regraphs it as a new function. And it finds this area and it just reorients it to now that I can use the fundamental theorem of calculus to solve it. Can't use the fundamental theorem of calculus of this, can here. Alright, again, we'll look at some examples and I'll show you the pictures that relate the areas. Alright, so this is going to be a first example. Alright, so suppose I want to find the area bounded by the curves f of x and h of x. Alright, so h of x is the function x squared minus 4. F of x is the function x squared plus 4. Alright, I'm interested in between 2 and negative 2. And it should be fairly obvious that f of x is always going to be bigger than h of x, right? Because I'm subtracting 4 from x squared here, and I'm adding, so there's always going to be an 8-unit difference between them, right? And so this is always true, alright? So it's always true, so it's true over the interval I'm looking for. Alright, and if you need your calculator to graph these, you can. These are very simple functions, though. This is just the x squared function shifted up 4 units. This is just the x squared functions shifted down 4 units. And so when I graph it, and you can check on the calculator if you want to, they should be parabolas. The first one starts at 4, and then again it's your parabola that opens up. Right, so that's f of x, which is x squared plus 4 at 2 and negative 2. Well, when I plug 2 in, that becomes 4, so this would be at 2, 8. This would be at negative 2, 8. Alright, and then I graph the other function, which starts down here at negative 4. And again, it should have an identical shape. When I plug 2 in to the h of x, which is x squared minus 4, it's at 2 and negative 2. Alright, and so again, it has this shape. Oops. Should go through 2 there. And so the area I'm looking for is this area. Alright, this is the area I'm trying to find between 2 and negative 2 and bounded by my 2 functions. Alright, so this is the area I want to solve for. Alright, I want to find the area that's bounded by f of x and g of x from 2 to negative 2. Alright, well again, I can't do that directly. Alright, I can't. But what I can do is I can set it up so that I can create a new function that'll find me the exact same area using the fundamental theorem of calculus. Alright, and what I do is, well, I know f of x is greater than h of x, and so I know if I integrate over the same values from 2 to negative 2, and I take my bigger function and subtract away my little function, it'll find the same area, but it will reorient it to where I can use the fundamental theorem of calculus. Alright, and so I'm going to type in my functions, or write in my functions, and then simplify. So f of x was x squared plus 4, h of x was x squared minus 4. And make sure you're careful. Distribute that negative. And so that simplifies to x squared plus 4 minus x squared plus 4. And so the x squareds cancel. That actually simplifies real nice. Alright, so a simple constant function 8. Which I can solve that fairly easily. I don't have to graph it and solve it. Alright, I know that if I solve this, it'll find this area. Now before I go to solve it, I'm going to explain what it's doing. Alright, so what I have here is when I take f of x and subtract h of x, it equals 8. Alright, so it's a new function, which is just a constant y equals 8. That's the new function. Alright, so 2, 3, 4, 5, 6, 7, 8. Alright, there's my new function, f of x minus h of x, which again, that's what I did. I took f of x and subtracted h of x, and it just simplified nicely. I did it on purpose, so it came out to a nice function, so you can easily see the area. And I want to integrate it from, I only graph the positive part of my function. I want to graph it from 2 to negative 2. Alright, and so this is the area I want to find. This area is a nice rectangular area. It's the same as this area up here. So even though the shapes are different, the area is the same. It's the same, just like when you have a 2-liter bottle, it can come in different shapes, but the volume's the same. You get 2 liter, whether it's in a weird shape or a nice shape. Same thing here. I get the same area, whether it's in this weird kind of shape or in this nice rectangular shape. And I can find that area. Actually, you can find it without solving the fundamental theorem of calculus. I'm going to solve it using the fundamental theorem of calculus. I'm going to find this area using this integration. Well, the antiderivative of 8 is 8x, and then I'm going to integrate it from negative 2 to 2. And so I'm going to take 8 times 2, subtract away 8 times negative 2, and so I'm going to get 16 plus 16. And so 32, or you could just multiply. This distance here is 4, this distance here is 8, 4 times 8, that area is 32. And so that means this area is 32, right? The area between my two functions is 32 units. All right, so the area between f of x and h of x over the interval -2 to 2 is 32 units squared. All right, and so that's what we're going to do. And so we're going to look at this. We're going to expand the idea in the next section, where we're going to add a step to this. We're going to find the area completely enclosed by two functions that intersect at most twice. All right, and that'll be the next set of notes.